Let's do a quick review on the molecular structure of water. Okay, so here's the formula for water, so 2 hydrogen atoms and 1 oxygen atom. Now let's draw the Lewis dot structure for this. Okay, so we first need to know the total number of valence electrons. So each hydrogen, so valence electrons is going to be equal to 2 hydrogens. Each hydrogen has 1 valence electron, so 2 times 1, plus 6 valence electrons for oxygen. So 2 plus 6 equals 8 total valence electrons. Okay. All right. Oxygen we'll draw as the central atom in this. All right. We have hydrogen over here. The hydrogen's flanking. We draw a bond in between the oxygen and both of the hydrogens. Okay, so that accounts for 4 of the 8 electrons. We're still missing 4 electrons, and we draw those as lone pairs. Okay. So if we analyze the structure of this, right, using, for instance, VSEPR, right, we can think of this as the lone pairs are going to alter the geometry. So we can think of starting this as a tetrahedron, right, where we have hydrogens here, it's there, and then we have a lone pair coming towards us from outside the board, and then going away from us inside the board. Okay, and then, of course, these, when we consider the actual geometry, we're not going to look at the lone pairs. We're not going to consider them in our geometry. We're just going to look at the hydrogen, oxygen, and hydrogen atoms, right? And so this is going to have a bent geometry. All right? And because the lone pairs cause repulsion, this is not going to have the typical bond angle. So if this is, or this is not going to have the typical bond angle of, say, for instance, a tetrahedral geometry. So it's going to be the bond angle for water. The HOH bond angle is 104.5 degrees. All right. So those look weird. So let's bring those in. All right. That looks horrible, but okay. So there's water. All right. And then let's look at the bond length, right? So if we think about this as having, for instance, 2 spheres of hydrogen, hydrogen, and a bent geometry, so H, H, O. So if we assume no bonding, right, we would be using, for instance, the van der Waals radius for oxygen and hydrogen. So the van der Waals radius for oxygen is 1.4 angstroms. All right? And the van der Waals radius for hydrogen is 1.2 angstroms. All right, so we would, if there were no interaction between this oxygen and this hydrogen, we would expect 1.4 plus 1.2. We would expect the distance between the center of masses between the oxygen and the hydrogen to be 1.4. We'll call this the radius, the van der Waals radius for the OH. 1.4 plus 1.2 equals 2.6 angstroms. However, there's bonding, okay? So there's sharing of electrons between the oxygen and the hydrogen. And so the actual observed distance is 0.958 angstroms. So much less than we expect. That's the radius of the covalent interaction, okay? So we have bonding between the oxygen and the hydrogen as evidence by the large decrease in the distance between the oxygen and the hydrogen for the actual molecule versus what we'd expect from van der Waals radii. Okay? Now, we looked at the structure, right? Recall that because of this structure, we have what's called a permanent dipole. Which means that the molecule has a positive and a negative end, right? So this is dependent on the electronegativities, right, the electron affinities of the atoms. And as we know, oxygen is going to have a larger electron affinity than the hydrogen. So this pulls the electron density towards the oxygen, which means that there's more negative charge on the end of the oxygen for water versus the hydrogen on the side of the molecule with the hydrogens, which is going to be partially positive. Okay? So that means there's what's called a permanent dipole. We can denote that like this, all right? Which is, we denote with this where there's a plus sign at the positive end, and then we draw the arrow towards the negative end, all right? So why that's important then is because this can interact with other molecules that have permanent dipoles, and it can also, in fact, which we'll talk less about, it can induce dipoles in molecules that don't have one, all right? But importantly, let's stick to how it can interact with other molecules with permanent dipoles. So the easiest way to think about this is, again, we return to an interaction between water and water, right? So if we have one water molecule, with a partial positive and partial negative end, right? We have these lone pairs, which help to sort of visualize this interaction, right? We can form hydrogen bonds, almost like magnets, where the positive end of a second molecule of water interacts with the negative end here, okay? But we also have, in this special case of hydrogen, right, we also have what can be thought of as a sharing of this hydrogen atom between these two water molecules. And so this is, in addition to the dipolar interaction, we also have a hydrogen bond. Okay. And as you might have seen before, this ability to hydrogen bond is important for the very high boiling point of water, the very high surface tension of water, and then also a number of very important features of water, which are important for biological life. For instance, such as, we'll get to this in a later video, but for instance, the ability of ice to float on water, because ice is less dense than liquid water at cold temperatures, right? So this, the hydrogen bonding is critically important for a number of features, and we'll come across the hydrogen bonding of water to other hydrogen bonding to other biological molecules and with itself many times as we go through this course.